Start. So welcome everybody to the webinar of today. The speaker of today is Kerstein, and he's going to talk about economical turbulence simulation using map-based advection. So as usual, I introduce the speaker very briefly, and then I leave him the floor. After completing his PhD in applied statistics at Princeton University, Dr. Kerstein worked for 35 years at Sandia National Laboratories in Livermore in California. He joined the combustion research facility at Sandia shortly after its establishment, and later was appointed as a distinguished member of the technical staff. There, he applied statistical technique to a broad range of combustion, thermal fluid, and material science problems related to spray combustion, coal combustion, and solid propellant combustion. Additionally, he made fundamental theoretical and modeling contributions in the field of turbulence phenomenology. Dr. Kerstein is a fellow of the American Physical Society and a past member of the editorial board of Physical Review. He has authored and co-authored over 130 journal publications. He has served on the Scientific Advisory Committee of the CIDAC, Computational Astrophysics Consortium, and the Center of Environmentally Friendly Energy Research. Since his retirement in 2012, Dr. Kerstein has served as a consultant to academic and research institutions, and he has continued his broad engagement with research communities in his areas of expertise. So it's great to have here Alan Kerstein for the seminar of today, for the webinar of today. So Alan, I stop sharing my screen, and you can start sharing yours.
Okay, well, let me, share screen. Now, let's see.
There we are, we see your screen.
Yeah, I'm going to go to full. Okay, good. Okay, well, thank you very much, Francesco, and for the opportunity to talk about work that I've done with a large number of people. I'll be acknowledging further along in the presentation on the subject of a turbulence modeling approach that uses the concept of map-based advection. So the very first thing I need to do is to explain to you what map-based advection is. It's just a little delay here. My arrow is not doing what it's supposed to do. I'm just going to stop sharing for a second because the arrows are not working as usual. So this back up here. Works differently when I use screen. Okay, let's see. So now I get to screen share again. I think I'll stay in this mode instead of going to full screen because it doesn't seem to advance my slides when I'm in the full screen mode. Okay, so what is map-based advection? It's, in its broad sense, it's a familiar concept. There are hybrid Lagrangian or Eulerian schemes in which the advective advancement is done in a Lagrangian manner, by which I mean that the advection is advanced by displacing the faces of individual mesh cells, while the Eulerian advancement within the time advancement cycle is done by conventional Eulerian time stepping of everything but advection, such as viscous transport. In the modeling, I'll describe the concept of a map-based Lagrangian approach is used as a physical modeling construct to obtain highly reduced representations of turbulent phenomena. In particular, it allows reduction of the turbulence treatment to low dimensions, and here it's illustrated in its 1D implementation. So I'm going to run turbulence simulations just on a 1D domain. And the individual unit of turbulent advection is what's called here a triplet map. And I hope you're seeing the cursor here. It's important. The triplet map consists of the selection of some interval along the 1D domain. And within that interval, which you might think of heuristically, as you can see in the illustration below, as the area occupied by some eddy. Of course, here I mean just a linear interval. And you take whatever function of some, say, scalar field C is within this interval. And here I show it as linear, it could be anything. You compress it by a factor of 3, put 3 compressed copies within the interval, flip the middle one, so everything ends up continuous, notwithstanding the discontinuous derivatives. And so that's the triplet map, the essential unit of advection in map-based advection. It's useful to look at the spatial discretization of this continuum treatment, as shown on the upper right here, where it's shown that it can be treated as a permutation of fluid cells. This makes it completely transparent that, like incompressible advection, you're conserving all properties within a fluid element. That there's no change in them, and that's what advection does. It simply moves stuff around, but doesn't change their properties in the Lagrangian frame. Now, aside from this heuristic motivation in the lower left, there are many good properties of the triplet map that I'm going to be showing in future slides. I won't say it's necessarily the unique or optimal choice, but you'll see why it's a good choice. And just as a little heads up, wherever I point out a property, in particular, an exact property of the behavior in a particular case, if it's in a yellow highlighted background, that's something that's exploiting unique properties of the triplet map, somewhat justifying why we make this choice. This choice is also a consequence of a general guiding principle in other aspects, in fact, all aspects of the modeling described that I'll describe, which is scale locality. This is an empirical but pretty solid phenomenological principle of turbulence, namely that an effect seen at a given scale has a cause at a roughly similar scale. In the same sense here, we have increased the gradients by a factor of 3. So we've taken a factor of 3 jump in gradients. So that's order unity. We haven't taken a factor of 100 jumps. So that's an illustration of trying to be as local in scale as we can in all aspects of the modeling. So that was a 1D illustration. Now we're going to look at the map, how the map operates on a 2D scalar field. So I'm just going to take this square and we're going to apply a triplet map to the whole area. You can imagine this is just a cut through a volume, so you're even doing it to a volume. Compress, copy, flip, and you can see how you end up back with a smooth function over the whole area here. And you see the continuity, and you see, and also measure preservation, which is the generalization to any dimensionality of the solenoidal nature of the flow, means that any color range occupies, in this case, same volume or area as originally. So the overall scheme resembles the description I gave you of the hybrid Lagrangian or Eulerian. Namely, you have time stepping in the background, everything but the advection, and these little tick marks represent the fact that this time stepping of these other processes is interrupted whenever it's specified in order to perform one of these instantaneous triplet map events. And the event is characterized by a size, as I indicated previously, a certain interval. But also, it doesn't have to be over the whole domain. It could be over an interval. So the location of that interval, as well as its size, is a parameter of it. And then, of course, it's a sampling of the occurrence times. These can be sampled either from prescribed distributions fixed in time, or very importantly, dependent on the current flow state, hence time varying and creating an important feedback mechanism between past history and what happens in the field going forward in the future. So for the first case study I'll introduce, we only do the advection, so there's no concurrent Eulerian time stepping. We're just going to hit some system state over and over with triplet maps and in some sense randomly sampled and see what happens. So what is this this system that we're it doesn't want to advance again. Let's see. Oh, problem is I have to have the cursor. I found the secret. The cursor has to be in the frame in order for it to advance. Okay, so we all learned something today already, whatever else comes up. So we're going to simply advect zero inertia particles. And we're going to consider finite sized particles so we can have collisions and coalescence. But for the moment, it doesn't matter if they're finite size or points. Okay, so let's play the same game as we did in the 2D picture. We take this square, we compress, we copy, we flip middle copy. So what's wrong with this picture? I told you that the triplet map just preserves all properties, but we ended up with 3 times the number of particles we started with because we have 3 copies of each original particle. So what's the problem here? Well, let's go back to the permutation picture and imagine that we start refining it to smaller mesh sizes. We can ask what happens in that limit, because we really mean the continuum triplet map to represent the limit case as the refinement goes to 0. Well, it turns out that one of the nice properties of the triplet map is it allows a direct, exact application of Borel's normal number theory that tells us that the consistent continuum limit when you're advecting particles is for each case where you have 3 images of the same particle, randomly pick one of them to keep, throw away the other 2, and do this random choice independently for all the particles. Okay, so this tells us the true consistent way of in the continuum advecting triplet maps, advecting particles with these triplet maps. Okay, so what is the numerical algorithm? The system state is just a list of particle locations, which we can initially randomize or whatever you want. Okay, each map affects, updates the list of locations. Here I applied the map to all the particles. We will be applying it to just subvolumes or subareas of the particles. But whatever particles are affected, the map does nothing but update the affected locations on this particle list. So we're playing a very simple game here. Okay. So if we do one map on the whole domain of some 2D system, this just shows what particle displacements might be. Okay. Now, so we did a map in Y. Now we did a map in X. Okay. So now we have what looks like a lot of trajectories here. However, you'll see that if we adopt the trajectory interpretation, that when we go to low dimensions, such as 1 dimension, we're going to have unphysically large number of collisions, because on a 1D line, a finite size particle can only immediately has to collide either with the nearest neighbor to the left or right. So it's very important, even though these lines are drawn to guide the eye, that we think of it as a jump process. So a particle is here, it just is taken away, it disappears, and it reappears here. And never mind the trajectory. Let's not worry about whether this is good physics. Let's just talk about what results we get from this, okay? So there was a direct numerical simulation of just tracer particle collision and coalescence by Beck et al. You'll see the really important thing from the modeling viewpoint we're discussing is the theory of what they observed. But first, I'm going to start with how do we reproduce the map-based advection version of this DNS. So it's a cubic domain. The side of an edge is turbulence integral scale, periodic boundary conditions. Each map is applied within a subvolume, L by L by S slab, okay? Where we consider the shorter direction, S, as the direction corresponding to what we consider to be the eddy size, because that reflects the maximum size of any possible displacement, because we're going to displace in direction S. The map can be anywhere in direction S, so that's the business that we have freedom to assign the position, we'll do it randomly. Now, the thickness S is sampled within a range from what we consider to be the Kolmogorov scale up to the integral scale, and the frequency of maps of a given size, it has its size dependence that is based on inertial range scalings. So far I started out talking about just an advective scalar field. Then I went to particles. Now I'm back to scalars, and the reason is we're going to find a very important connection between advective scalars using the triplet map and this particle system. Now, when we advect the scalar, as I described in the last slide, where we're picking from a size distribution of maps that obeys the inertial range scaling, and necessarily, since we have a scalar field here, it's diffusive, we now do have the time stepping of the scale diffusion equation between these maps. We have what's called the linear eddy model, LEM. So you're going to see that terminology, okay? And we're going to discuss the intermittency of the scalar field, and where the relative diagnostic is so-called structure function. Again, we have this C of xt, which was on one of the early slides. But we say, what is the difference between the C values at two locations separated by a distance r raised to the nth power, and then we take the ensemble average? Well, the scaling property in the inertial range is it's a parallel on r with an n-dependent exponent. In particular, if the Kolmogorov scaling laws, but without intermittency, say that this exponent is linear in n. Now, the analysis of the linear eddy model, as I've described it, by these two authors, which exploited specific properties of the triplet map, came up with this exact formula, which they validated by numerical simulations as being the correct formula for the linear eddy model. And the characteristic of intermittency of a scalar, or even in a velocity case, is that these exponents are sublinear in n. And here you can see a sublinear dependence on n, indicating that the map is the linear eddy model inherently encodes this structure function intermittency, which is not too surprising because it is a multiplicative random process, and so-called random multiplier distributions are one of the paradigms for representing intermittency. But in any case, we have an exact result here. Now, for large N, this somewhat exceeds DNS results, but it's pretty good for lower N. In fact, overall, it's a better agreement with most recent DNS than any other of the models that I'm aware of. Maybe there's a better one somewhere. So, but regardless of that, now, why did I bring this up? Because I said the Beck theory is very important. So I have to tell you what system they're applying the theory to, okay? They start out with some random system of monomers, okay? We just start triplet mapping them, as I said, in random directions, and I told you how the size distribution. Okay, we're doing it in 3D just to be like, to imitate the DNS. So at first we have, I haven't shown you all the way time zero. There's log plots. I can't show you time zero, we start it with all monomers, and then as we have collisions and coalescence, we get dimers, trimers, and so on. So what did Beck et al. Show? They said that the time growth, okay, it's log, so we're looking for a linear development here. The growth in time of the nmer number density for any n. Well, I use the subscript I, so it's Imer here. Is a power law in time where the exponent depends on the third order scalar structure function. And it's quite an elaborate theory in their paper that derives this result, okay? Now the third order structure function from measurements is 0.82. Well, the model, just using that log formula, gives you 0.84, which is pretty good, but we're not worried about measurements now. We're just trying to see if the model is a consistent rendering of the underlying theory. So we'll use the model value of this. And those are the blue line segments here, showing you that the prediction is obeyed. Okay, so, all right, I'm just giving you a moment to think to yourself, what do I think is going to happen if I run this simulation in one dimension? In other words, just particles on a line, hit it with these triplet maps, as I showed, on the earliest slides, and then just watch the coalescences based again on a jump process. Okay, I don't know what your guess was, but here it is: the models versus the theory. It works just as well, showing that the fact that it's a jump process rather than trajectory results in the physics being essentially dimensionally independent. So what this tells us is, in a certain sense, the theory, and also elaboration, it is specifically and very intentionally of a 3D nature, has a realization in physics that's somehow equivalent in this elementary 1D process of playing this simple game. And so I think that's an interesting inference in terms of what is the ultimate nature, underlying nature of the physics governing the particular process, governing intermittency and turbulence in general. I'll just leave that as a question hanging in the air. Now, another prediction of the Beck theory that was validated also by the DNS is that if you consider the time lapse from formation of some dimer until another monomer collides with it and forms a trimer, well, that time lapse is a stochastic variable that has a PDF. And they said in the inertial range of time scales, the exponent, there's a power law dependence in time of this PDF with an exponent that, and again, depends on this third order structure function exponent. We put in here the model value of this, and here's the comparison, okay? In particular, 3D result is shown here. Okay, so this basically recapitulates some of the points that I've mentioned here, and some of the implications, but we're going to move on, and we're going to add a little bit of physics. Okay, so here's a repeat of our earlier zero inertia illustration. We're going to introduce particle inertia. Okay, so the zero inertia particle has, for a given triplet map, some displacement resulting that's lowercase delta. We're going to replace that by a displacement by uppercase delta, which is the non-inertial displacement times 1 plus s, where s is the model analog of Stokes number. And we're even going to consider polydispersion, where s can be different for each particle. For discussion purposes, we'll take s to be positive and the results will be based on that. It's really not essential, but it's good for all particles to choose one sign or another just because of some analysis that's going to follow. Okay, so now we just start with the randomly distributed particles, and we start triplet mapping, but with these extra displacements. Now, the red dots are the non-inertial, s equals 0. The blue dots have some inertia, s equals 0.1. And also, I want to say this is going to be a different physical regime. We're going to suppose that the entire domain represents a Kolmogorov scale. So we're going to be, for our example case, be discussing actually the dissipation range. So we're always going to map the entire domain either in x, y, or z direction. So there's no variation in the map in terms of the mapped region. It's going to map all particles. And so, but the physics is that the physics of the dissipation range. But what's noteworthy in this plot, you have to squint a little bit, but you can tell that I hope that the blue dots cluster to some noticeable degree, whereas the red dots do not. Okay, but aside from this, let's first understand why this is happening. So the zero inertia case can also be discussed in terms of a continuous scalar field, which is the particle number density. So it's some filtered or ensemble average, but locally defined number density. If we take this, compress it, and copy it, we get three times the number density. And if we remove 2/3 of the particles, as I told you we have to do, we come back where we started. Nothing exciting happens here. So if we do the non-zero inertia, well, everything that's mapped into the leftmost image is compressed a little bit to the left, so it occupies a little bit less than 1/3. Likewise here, it occupies a little less than 1/3. Because we're flipping over, the middle image always involves flipping spatially in the horizontal direction. We end up expanding, so we can pretty much understand why this is. And so this again is a case where the triplet map in particular here gives not an exact mathematical result, but at least gives us an intuitive interpretation. However, in terms of a truly mathematical result, we look at the so-called radial distribution function. It's likelihood that if you're sitting on a particle at some distance r, you're going to see some other particle. And because it's conditional on sitting on a particle, you're going to increase its value if there's clustering, and if the distance r is small enough so that the clustering is increasing the local number density. So it turns out that exploiting specific properties of the triplet map, it can be shown in an exact analytic treatment that in a given range of R required to obtain a leading order result in perturbation theory, G has a power law in R that's bilinear in the Stokes numbers of the two particles. This has been heuristically justified. I mean, even the previous slide somewhat serves to motivate that. but it's also been seen in DNS, but there hasn't before been some realizable systems and realizable mathematical system that can recover this result exactly. So this is a novel aspect in this context. So, well, without belaboring this, I just want to make the point that in addition to being an area that brings up some interesting points of principle about map-based advection, this particle treatment using triplet maps turns out to be a practical tool for studying processes that are relevant in cloud studies, even in subgrid closures related to cloud studies. And this is also, this observation is also a convenient transition to what's going to come next, which is the fact that those cloud studies and a lot of other applications are really more focused on continuum scalar fields rather than the particle advection. And this is just a sample of some of the topics to which linearity has been applied. So now we're going to switch gears and try to get more ambitious in our modeling. We are going to try to simulate the following setup. So it's a buoyancy driven process. We start out with a fluid. I mean, in the laboratory, it'll be a liquid. So it's initially at constant temperature. Now we can vary the fluid density either by varying the salinity or the temperature. So the warmer it is, the less dense. But the higher the salinity, the higher the density. So to get a stable system, we have decreasing density initially as we go up vertically upward. And we start with constant temperature. Okay, so it's a stable system. We start heating it from below through the solid wall. What happens? So we have some temperature come in here, which lowers the temperature contribution to density. Now we have a gravitational instability, so we initiate convection, it can become turbulent. Turbulence can result in mixing and therefore homogenization of some zone. If we homogenize what was originally this linear slope profile here, we're going to end up with a, in the ideal case of no vanishing diffusivity of the salinity, we'd find an absolute discontinuity in a plateau jump to the original initial condition. Well, the salinity has a finite but very small diffusivity, so we get something like this. But then we have a new barrier to advective transport because of this, as you see it here, the full density due to this density jump. So but we do have the temperature now diffusively leaking through. The process starts anew, so we end up getting a new gravitational instability. So then we get another convective zone, and we build a staircase. Okay, so how are we going to model this? Well, our 1D domain is going to be in the vertical coordinate z, and we're going to have a density profile that we're going to be involving, but we're not directly, but we're just going to evolve the salinity and the temperature, and from that we just figure out the density based on the just the thermodynamic laws that relate the salinity and temperature to density. And so we're going to have Lagrangian advection of this salinity and temperature by triplet maps. But here's what's important. I mentioned before that when you sample maps parameters, you can either do that based on prescribed statistics or statistics that depend on the system state. Now we're choosing the latter approach, and here's how we do it. So we have some, let's say we have a gravitationally unstable density profile, heavy over light, okay? So we have all manner of triplet maps that we might consider implementing. at different locations, Z1, L1, Z1, Z2, different map sizes, L1, L2. How are we going to sample from them? Well, we want to find, if we're sampling events, we need a time rate of their occurrence. So we're looking, a time rate means we're looking for a frequency. Well, we have at hand the buoyancy frequency, okay, but it's typically denoted N. And how do we compute it here? Instantaneously and locally for a given map that we might implement. Well, we consider what is the map-induced decrease of gravitational energy, potential energy per unit mass. So we just have to look at the what this profile looks like before and after a triplet map, and you've already seen some illustrations, so you can kind of imagine what the density profile would look like after the map, and we can easily figure out the change in gravitational and potential energy. That's all we need to figure out the local instantaneous buoyancy frequency. Now we can take this frequency and we can just formally construct a mapping rate distribution, this lambda. So now what we'd like to do is sample from this mapping rate distribution. But because the system is constantly evolving with every operation, whether it's a triplet map or whether it's a diffusive time step, we keep changing this distribution, which would be prohibitively costly to keep computing its value for every possible Z, L, and T. But there is a so-called rejection method, which is basically a guess and check approach, which makes this affordable to end up time advancing the system with this transient and Z and L dependent rate distribution. I'll also comment on two things. One is that viscosity enters in here because we say that some viscous threshold that the gravitational potential energy has to exceed in order to actually be able to force an instability to happen. And the other point is there are a couple of constants here, and they're not tuned to the case at hand, they're tuned based on Rayleigh convection, but it turns out for the normalized properties we'd like to look at, the dependence on these constants often is factored out, and that is the case in the results I'll be showing you. So we run the simulation and we do get, as described, these staircases growing, shown in here, and you can see sharper jumps for the selenium as opposed to the more diffusive temperature. And here's the overall density, and you can see the inversions there as I described to you. It's just a snapshot from a simulation that's run. And then we can do a lot of quantitative things have been done to post-process these simulations. Just one example. So just setting up a case where you have one quasi-steady interface of the sort of described to you. And what we're looking at is as a function of the ratio of the density jump caused by salinity divided by the density jump caused by temperature, well, the absolute value of this, you know, the more of a salinity jump you have, the more stable you have. As a function of this, what's the ratio of salt to temperature flux across the interface? The symbols are the simulation results. We have measurements here, we have theory. There's a lot of physics going on here. The only point I'm trying to make here is that we do get quantitative, meaningful results that capture the phenomenology. It'd be great to talk more about it, and what I want to move on to other cases. So DPE is clearly a reasonable model, to say the least, for staircases, but it has some limitations if we want to take it any further. In the real world, potential energy decrease requires some compensatory energy change, which in this case would be converting a potential energy to kinetic energy, but unfortunately, the model DPE does not do this. So you could say, well, it's as if there was immediate viscous dissipation, and in Rand's world, you'd call it the production equals dissipation level of treatment. So what we do is we introduce in what I call one-dimensional turbulence velocity profiles. They, like the salinity and temperature profiles, is subject to fully resolved molecular transport. In this case, Fickian fixed law basically, but in this case, of course, it represents the viscous transport. The map sampling rate still involves buoyancy, but in a somewhat analogous way. I won't really go into the details, but there are ways of quantifying the shear, which is, again, a rate. It's an inverse time to a characteristic shear within the eddy range. And you can combine these things and end up with that lambda, that eddy rate distribution. But now we also want to implement within the ODT the actual kinetic energy, and if applicable, momentum changes, and actually modify the velocity profiles to reflect the fact that the loss of potential energy really did create kinetic energy. Okay, so we're adding kinetic energy to these velocity profiles. This is not advection, but that's okay because the true momentum equation does have a pressure gradient term that can add or subtract kinetic energy or momentum. So it's really appropriate to add this. So now we speak of an eddy event because two things happen during this event now: a triplet map followed by this kernel application. So I don't know what the magic is. Sometimes it doesn't want to advance, and sometimes it does. Let's see. Okay. So here we have, so we can put aside buoyancy now and discuss pure shear flow. So here's just some streamline velocity profile as a function of some lateral coordinate. So we have some shear here. It can generate a triplet map. Of course, now we're talking about the complete eddy event, but this is just the triplet map part of it. You can see we've increased the shear. So that means we've just by how we construct the eddy rate distribution, we're going to have a higher rate of eddies that are contained within this smaller region. So in other words, we're having a dynamical feedback in the sense that if we've taken one step in scale reduction, we've increased the frequency or the probability per unit time that we're going to take a further step of scale reduction. So we have, in essence, an avalanche process, and in particular, it's the avalanche process representing the turbulent eddy cascade. Now, as in the example of the buoyancy frequency, the shear as well, it's basically dimensional analysis that we're using to set these rates. You could argue that really we're applying local mixing length theory, where the local mixing length is whatever the candidate eddy size is. And because of that, we're basically have a realization of dimensional analysis similar to what leads to the k to minus 5/3 scaling for the energy spectrum. So it's really not that surprising that we get that energy spectrum when we run, say, homogeneous turbulence simulations. I'm not going to show you that result. I want to go on to other things. But this just restates some things I've said, since we're using instantaneous flow states rather than average states. We are doing a form of mixing length modeling, but it's much more dynamic because of all the couplings that are involved between molecular transport eddy events. You can put in initial and boundary conditions, body forces. Importantly, the velocity profiles play a key role in establishing the shear structure of influencing eddy occurrences, but they do not at this point directly advect fluid. It's just the triplet maps that do that. Okay, so let's just see some illustrations of how this works. So this is Kelvin. Okay, before I get to this, what am I plotting here? So this is the simulations are time advancing. So here's time, and it's what I call an eddy space-time diagram. Each vertical line segment occurs at a horizontal location representing its time of occurrence, and its endpoints represent the eddy range. So this is, I call it a skeleton of the flow, because if you know all the eddy events that occurred since the viscosity is deterministic. You could reconstruct the velocity field throughout the flow realization. So, and we're advancing a fixed law for viscosity. The difference between these two is here we have a step function initial velocity profile. Here we have a top hat, which produces the distance, the difference between these. Now, it's interesting, you can see this clustering here. Well, oh, intermittency. Yeah, well, we talked about intermittency, but there's a different kind of intermittency. This is the so-called outer intermittency that results from engulfment of the free streams outside the mixing zone, which then leads to the high intensity breakdown of this engulfed fluid. This shows the model is capturing, in that sense, for these entraining flows, outer intermittency, as well as the inner intermittency that we've already discussed. Okay, so now I jumped ahead beyond those constant density flows to show you some results for Kelvin-Helmholtz, but with free streams of different densities, up to a density ratio of 8, simply because there's just a lot going on in these output statistics and showing how the ODT reproduces it. Again, these are normalized quantities, so there's essentially no dependence on the model parameters. So these are the mean velocity and density profiles. These are budget terms of the turbulent kinetic energy for two different density ratios. You can see there's some asymmetries that are captured because of the density difference. And it's just to say, well, the model that has, has some quantitative chops here, is the point here. Okay. Doesn't want to advance again, so I have to play games. All right, got it to work. So far I've shown you either statistically stationary flows or time developing flows, but we're more interested physically in spatially developing flows. Well, you could say, well, if I had a time developing jet, I could call dx dt times the bulk velocity, just handle it that way. One of the problems is that in the time developing flow, you have the same elapsed time of all trajectories going from T1 to T2 trivially. That's not true in spatially developing flows. And there's a whole lot of other reasons why you need to treat spatially developing flows differently. So what you do is, instead of advancing on the left-hand side using the UDT here, use U du dx. But now you also have to introduce, since you're now living in X and Y, because Y is the actual coordinate for the on which the model lives. So now you have an X and Y, so you end up having to introduce the 2D continuity with an auxiliary variable v that can be trivially obtained by solving the continuity that introduces a lateral flow. This is now going to be a real advection above and beyond the eddy events. And so what happens now, there's a lot happening here, because this is a buoyancy-driven flame, a lot going on here. But as far as the one point I brought up about the 2D continuity, so because of the buoyant forcing, the streamlines of velocity is increasing as you go upwards. So if you draw a control volume and apply continuity, you have more mass flux coming out at the top than coming in the bottom. So you have to have inward lateral velocity. And this shows, indeed, you see this necking. It's very obvious here. It's a little more subtle here. But the point is, if you did a temporal simulation of this jet, you couldn't possibly see the necking. It just shows we're getting extra physics resulting from this. So, okay. So here's, we're going to add a little more physics. Now we have a buoyancy-driven flame where the fuel is emanating from a wall. So we have a boundary layer, buoyancy-driven boundary layer, which is interesting because it has a non-monotonic mean velocity, vertical velocity profile. And this is just to show that, can introduce a lot more physics. Basically treat multiphysics problems. Now, this in the previous case, they have validations and so on, but I'm not getting that point because we want to move on to other things model can do. We can go to curvilinear linear coordinates. We can do surface tension, which can and have done, I should say, surface tension with immiscible fluids, shocks, and so on. But I do want to highlight this. This is another exact result that's a consequence of the using the triplet map specifically for stably stratified shear flows, that the critical Reynolds number is 1/4. And then there's all manner of other things been done with the model. I know that there's not too much time left, so try to move on and cover just in the last few minutes. Change gears completely. Okay. All right. Forget everything you've heard. We're starting from a blank sheet of paper. Let's say we have an LAS that's just scalar mixing. Of course, you want to do this for reactant flows or what have you. So a typical subgrid model is that in each LAS cell, we have a collection of fluid parcels, each of which, this is composition space, each have different compositions. So to model mixing, so-called curls model, we're just going to randomly choose a pair of these parcels, and we're going to mix them. We're just going to do this at some rate, and of course, the system's going to overall homogenize. Okay. Now, what's the real physics here? In truth, it's the if we want to get some of the physics of spatial structure and at the subgrid, we have to remember why are particles that are relatively close to each other more alike in their thermochemical state? They've never been close enough yet to diffuse, let's assume. Well, the reason is because during their time history, there have been third party and fourth party and so on collisions where, or at least close approaches where they could exchange their contents with other particles that are moved back and forth. So by the time they get here, there's already been some information communicated that these two should have become somewhat similar in their states. Okay, so how can we just take this collection of particles and simply decide which pairs should be allowed to mix in a way that somehow captures this physics? And so we get some notion that there's spatial structure reflected, in particular the spatial structure of turbulent flows in the inertial range, or whatever going on here. So here are our parcels. Okay, now we introduce a tree structure, or so-called ultrametric structure. People have built these so-called ultrametric or even shell models. Now, sometimes those things have, or I should say, probably in all cases, but this one, they use different levels of filtered representations at the different levels. Here, the only physical particles are at the base of the tree. This whole thing is just a big mnemonic to tell us when and where to mix parcels. We say that only parcels connected at the lowest level of the tree are allowed to mix. In fact, as soon as parcels that are dissimilar become connected at this lower level, they mix. So there's never, except in an individual instance in time, dissimilar particles, that are connected at the lowest level. So how do they come into contact? Well, we do swaps. Now, these black circles represent the nodes of a swap. We go 2 levels down, we pick a subtree, we swap them. Then we have 2 dissimilar things connected at a lower level, connected at a lower level. We get 2 mixing events. But a swap with this, it starts from this apex. We pick this, we swap them. We haven't created any dissimilarity at the lower level. So there's no mixing induced. So you could see this it creates some hierarchical character where if you had complete segregation, these were all water and these were all lemonade. There's no swap initially that can create a water lemonade pairing that'll just get dilute lemonade. You have to get a higher level swap to basically break down what's called in the chemical engineering the scale of segregation. And so you have to have some kind of hierarchy. In other words, you have to have a cascade, and only at the termination of the cascade can you actually mix these things. And that, in fact, is what I've just described is the essence of the phenomenological description of a turbulent mixing at a elementary level. So you can play similar games to what I've described already, as in LAM or ODT, prescribed sampling rates, put in velocity profiles. I should say velocity as one of the properties of the system, and then in fact you can introduce wall parcels and do then you can get boundary layers. A fun fact is that when you I showed you this hierarchy. Now this hierarchy has to involve a spatial refinement factor in order to start quantifying things. And it turns out, just by sort of the same reasoning as in fractal box counting, you can obtain an effective dimension that's a function of this factor A. Well, this factor A is a real number. So now the effective dimensionality can be any real number, positive real number. I'm not saying you're going to go down to like minuscule 0.001 dimension as a practical matter, but it is interesting here that we're now even freed from the requirement that the dimension is an integer. And the model does non-trivial things like you can, with a few more rules, get a channel flow situation, a simulation, which does nice things. This is the DNS versus model, instantaneous PDF of the instantaneous wall stress normalized and other things, turbulent kinetic energy budget. Anyway, there are other fun things in this. I'm skipping on, I've run out of time, so I'm going to stop. I was going to show like a little fun physics discovery example. The people who did the work probably recognized their slides. Sorry, I didn't have time to show them. But I just want to thank all the people here. I shouldn't say all, I'm sure I forgot a few people, but it's been a fantastic journey together with you. And I thank you all for listening, and I welcome questions.
So thank you, Alan, for the very interesting talk. So as you just said, let's open the stage for questions. So whoever would like to ask a question, just feel free to unmute your mic and ask a question, or you can write in the chat. I can report it. Yeah, then I don't see anyone for the moment. So then, Michael, go ahead, Michael.
Excuse me.
Yeah.
May I have a question?
Yeah, go ahead,
Yeah, thank you very much, Alan. It is very interesting. So, since I didn't see many formulas, so maybe I didn't understand, and so I'm very sorry in advance if the question will be a little bit stupid. So each in triple mapping, each mapping corresponds is represented by a certain turbulent structure. And you said that this structure can be sampled from the stochastically from a certain distribution. What kind of time distribution is used to sample each map?
Okay, so I need to go back to the one place where I really showed you in a relatively explicit way how this works was here, okay? So
excuse me, concerning the particles, because here I've seen the mapping, but concerning the particle.
Okay, see, with the particles, I wasn't doing it dynamically. I was just, okay, I understand your question, yeah. So it goes back to, I think it's on this slide. Okay, I said the S-dependent map frequency is based on inertial range scaling, okay? So if I have a given size map at a given, and it occurs at a given frequency per unit length. One of the things that the triplet map structure allows you to determine in an exact way is the diffusivity of the random walk that a typical particle will execute. Okay.
Mm-hmm.
Because all you're doing is displacing particles randomly. They have some kind of random walk, and if you tell me the map frequency of these maps per unit length, I can figure out how often a given particle is subject to maps. I can figure out the mean square displacement of such a particle. So I know it's, in effect, it's the diffusivity of its dispersion process, okay?
Mm-hmm. Okay.
Now, the inertial range scalings tell us that that diffusivity should scale as the, in terms of, the, like eddy diffusivity as the associated eddy size to the 4/3 power.
Mm-hmm.
And that allows me to back out a power law for what the map frequency should be as a function of map size.
Mm-hmm. Okay, and so somewhere the Reynolds number should be present, because according to Reynolds number, the structure is different.
Well, you see, I've kinematically imposed a Reynolds number because I've legislated that I'm going to choose a given Kolmogorov scale. So up to a constant, whatever the Reynolds number, the Reynolds number of 3/4 is L over LK. So the Reynolds number is L over LK to the 4/3 times the coefficient. So I've built in a Reynolds number here in a purely kinematic way.
Mm-hmm. Okay, thank you. And so, in fact, when you construct those maps, and for example, for Liouville space in phase space, it should correspond to some conservation equations. Okay. So, and here it is just a jumping, and that means that if, for example, I will apply this model in two-way coupling, then I will violate all laws of conservation.
That's such a great question, because I knew that such a thing had to exist, Liouville equation. I couldn't figure it out myself, but I had a very brilliant postdocs. I know someone in the audience know the guys I'll mention, Jackson Mayo, because he figured out the Liouville equation. Well, essentially, it was a functional Fokker-Planck equation, because if you run an ensemble, you see, to get statistics out, you might run either it's a time ensemble or you run an ensemble of realizations. And so you have a probability distribution. Now there's sort of an underlying implied master equation down there somewhere. And he just wrote down in a purely formal way what the functional Fokker-Planck equation is for this thing. And since you asked, I'll send you a paper that has an appendix written by him, where he's written down what the formal expression is for him. For that equation, and it's purely formal. It doesn't help you in any way except to give you an assurance that that there is a formalism that describes this.
Okay, thank you very much. Yeah.
Hello, Alan.
Hi, Christos.
That was a nearly lifetime work within an hour. You said so much. I have many questions, but I will ask one, at least one.
I insist on a finite number, but I'll compromise on it with a count.
Okay.
But I'll compromise with you. How about a countable number?
Okay. So you applied your model to the Kelvin-Helmholtz, and you started with some, I assume, a discontinuity, and you said you obtained outer intermittency. I'll ask my question provocatively, but it's not meant to be. Why is that non-trivial?
I'm not saying it's non-trivial. It's just it's just showing you. It's not really a non-trivial physical fact. It's just a convenient alignment with the known phenomenology, but it's really more to illustrate a point about the model that even though we're just sampling one eddy, you know, it's the whole system, meaning the whole thing is Markovian, because the current velocity profiles completely determine what the lambda is. Okay. However, from the point of view of the maps, the velocity profiles encode memory of past eddies. In this way, future eddies are affected by the medium of the viscosity of the velocity profiles and the memory reservoir of the past profiles, and that's the way that you ultimately get this clumpy stuff in the model. So I'm not going to claim that this outer intermittency is a non-trivial property. You know, it's only when I show you, you know, a plot of a quantitative diagnostic, you know, it's numbers versus numbers, that I say that anything possibly non-trivial is going on.
I think there's someone called Shama who wants to ask a question, so I'll let him ask a question and I'll return later. Thank you, Alan.
Okay, we're going to alternate. Yeah, okay.
Go ahead, Shama.
Hi, Professor Kerstein.
Hi, George.
So you already kind of know the two approaches I've been working on with ODT, the extension and acoustics. And today morning, I was talking to Lorna here, and we came to the point where we understand what is probability acceptance, though the role probability acceptance plays when we talk about the eddies and the way they mimic the hydrodynamics. Okay, so what we are thinking, if we can somehow include an acoustic filter at that point, like the probability acceptance at that point, which allows the eddies which are relevant to only the acoustic information, which I need in my case. Okay, so that would necessarily like just eliminates everything which is relevant to hydrodynamics, for example, and would only give me the eddies which are important for my acoustic information. This sounds really fancy when I'm just talking verbally here, but I was just thinking out loud here with you, since I got this opportunity, that do you think that would be something logical from your experience with acceptance?
It may only be a limited number of eddies that are ultimately acoustically relevant, but I do believe, you know, because of the whole cascade process and the interaction across scales, you know, like I said, scale locality, at any one step, it's over, you know, only a moderate scale, but collectively across scales, the whole population of eddies gives a lot of interscale interaction. I think the eddies that don't necessarily, strongly impact your diagnostic can still be important for the dynamics that determine the statistics of your acoustically important eddies. So I don't think you can eliminate them from the simulation. You might have a way of deciding that only a subset of those eddies really has to be, incorporated into your diagnostic.
Yeah. Okay, thanks.
Okay, so let's see if there are other questions. So once again, just feel free to unmute your mic if you want to ask a question or write in the chat. Go ahead, Christos.
Just return to another question very quickly. For the linear eddy model, you said that the structure functional exponent, I think of scalar field, was not quite constant, was log kind of
Right.
log behavior. Now, if it was constant, I guess that would mean that the field is dominated by discontinuities, I assume.
Yeah.
Is there a way to describe this exponent, which is log rather than constant, so very close to constant in terms of discontinuities or something like this in the field?
Well, when you look at individual realizations, you see you do see incipient discontinuities to the point where you could plausibly speculate that there may be true saturation, but it turns out that there is this subtle divergence. Just to bring everybody up to speed, are you familiar with this Ivor et al. 2018 DNS where they showed for the scalar, and I have a later paper they showed for the velocity that there is at least a plausible evidence at the highest n values that they're seeing saturation. Okay, so I'm not sure what more you're asking me about saturation and discontinuities other than that.
Okay, that's no. You just basically you answered that this function log of n does give something close to discontinuity somewhere in the field.
Yeah, I definitely thought that just from looking at realizations, they're jumping enough that you could really believe that saturation had set in, and so, because that is a very slow. But it's interesting. It's a slow process, but when you plot this function against the DNS, it's up to the highest n value that the DNS is showing. The log is still progressing, nicely upwards. I mean, I can't claim that this result is calling into question the DNS results, but who knows? These things are very tough, and people think they see something in data, and it turns out not to be the case. Which is one of the reasons it's nice to have a model that we can actually solve for it with the underlying theory. And another consideration is that the phenomenology of the model is very straightforward in this regard, because it's like I said, it's multiplicative random process, and and if it's linearity, it's just sort of Poisson. So so just with the most elementary building blocks of what could cause intermittency, you get a result that is sort of only marginally violating saturation.
Thank you.
Okay, thank you. So let's see if there is someone else who would like to ask a question. I do have a question myself that somehow relates to the question of Michael before. So when you talk about the particles, the advection of the particles, and then you somehow replied to Michael that basically the Reynolds number is embedded in the scaling, in the Lagrangian scaling, basically. What I was asking myself is, when you consider, for example, a chaotic mixing which is non-turbulent, would this technique, how does this technique apply, and in which is it possible to apply it, or we need actually an inertial range to use this technique?
First, I can give a shorter answer on the inertial range. You do not need an inertial range. The inertial range may or may not develop based on circumstances. In fact, when you do a buoyancy driven flow, like Rayleigh convection, there is a scale range where you see the Bolgiano scaling. See, because the model is, in other words, the model is responding to physics, and where the physics prescribes inertial range, the model can, hopefully in most cases will, correctly capture it. Now, on the question of chaos, that brings up some good points. I'd say this model is orthogonal to chaos, meaning there's no overlap. Because chaos and what this model is representing are two sides of the coin of turbulence. And the point of chaos is it's ultimately deterministic, and it's just such a degree of complexity within the deterministic order that it has this characteristic of chaos. But it brings up the point, let me think of the best example to discuss this. So what does the model give us beyond the inertial range? This entrainment, okay, this is another rendering that, it's not of course, there was a space-time diagram I was discussing with Christos. So, these puffs or lobes that you might say develop here, people talk about the coherent structures, these you can get actually in a buoyant fire, you can get this non-chaotic puffing, which actually is deterministic frequency. But of course, these things, if they're driven in a certain manner, these dynamical systems can then go through the period doubling, and you end up in the chaos and so on. Well, the model cannot see it as chaos, but it can develop just because of this eddy memory that I described, kind of these local degrees of organization, or you could say these emergent structures and emergent, mesoscopic phenomenology. But it's not. It's an interesting question as to whether it emerges at a scale large enough or of enough time duration so that it gets above the statistical noise of individual eddies and starts to have a little bit of an operationally chaotic character. And it's an interesting speculation. I've never explored it in that direction. Another, here also, see what's happening here. See, things are getting very hot over here in just a high temperature region. That means the viscosity is going up. Well, maybe that's suppressing the eddies over here, so it gets less turbulent. So maybe there was some, larger scale interactions that ultimately have a chaotic character emerging. Okay, are they reflective of any true chaotic character of turbulence, or are they, or is the chaos too sensitive to the difference between real turbulence and the model for the model to be describing it? I can't say at this point, but it's interesting thought to explore. I really haven't considered that, though. It's interesting. Thanks.
Yeah, thank you. That's, yeah, I mean, I was just thinking to the map you showed at the beginning that looked somehow kind of similar to the tent map, and that brings some universality into play. So that's
they could. It's because it is stochastic.
Yeah.
The maps could be anywhere.
Sure.
Somewhere. It's like the monkey that types Shakespeare. Yeah. Somewhere in some simulation, the triple map space-time sequence is going to just give little sort of transient bursts of chaotic behavior. But I'm saying even at a more mesoscopic level, the monkey might type Shakespeare and generate a little chaos. But at this point, I'd have to say any resemblance with the kind of chaotic behaviors of people, deduced from turbulence observations, simulations, whatever, would be speculative without really probing it. But it's an interesting thought.
Okay, thank you. Thanks a lot for the reply. And let's see if there is someone else who would like to ask a question. And once again, feel free to unmute your mic if you have any, or write in the discussion. That doesn't seem to be the case. So Alan, thank you a lot for the presentation of today. It was very interesting. You showed us so many examples of the application of the methodology, and so thanks a lot. I think we learned a lot of physics through your presentation. So thanks a lot. Thank you.
Okay, thank you. I really enjoyed it. I appreciate the invitation. Okay. All right.
So I invite the audience to thank our speaker again, and hope to see you soon next week.
Thank you.
Okay.
Thank you, Alan. Thank you very much.
Bye.
Thank you.
Thank you.